And one of my long-running hobbies is getting reflection into C++. So this is something that I, in some capacity or other, have been working on for the past 15 years. So that's that is what will be the topic of today's presentation. So how a potential reflection API in C++ would look like or could look like. We will see also some examples, and I hope you enjoy and that you will not be looking as confused as this poor guy. So in detail, we will be talking, we'll have a short introduction, what's reflection and what is the reverse of reflection, what are meta objects and metadata, and how could a reflection API be designed. As I mentioned, we will see some examples and use cases. So what's a meta object? Meta object is some sort of representation of some base level language entity like a namespace, a type, a function, constructor, or it can represent many different things that we deal with in.
Matúš?
Yep.
There's a bit of an issue with your sound. Can you switch to a different microphone?
Okay, so as I was saying, a meta object is some meta level representation of some base level language entity like a namespace, type, function, or something else that we regularly deal with in a C++ program. But unlike on the base level, on the meta level, all the meta objects, all the representations are reified. What does it mean? It means that the meta objects can be stored in variables, they can be used as function arguments or function return values. And this provides us with the ability to write more complex reflection algorithms or even libraries of such algorithms. And most of the reflection operations are invoked at compile time. So this happens when the program is compiling. And like as a matter of saying, we say that a meta object reflects that base level entity. So the meta objects provide access to metadata reflecting various things in the base level entities in the program. So for example, types of variables, data members in a struct, and so on and so on. There are like literally hundreds of pieces of metadata that we can get from the compiler and can use in some way in various use cases. So on the technical level, how would a meta object be represented? It can be a compile time constant value, and the type of that value doesn't need to be explicitly satisfied, or we are not even saying that every meta object needs to have the same type. So generally, we can, in C++20, we can define a concept which could be called meta object. What is the actual definition is not really important right now. It could be some compiler magic, or it could be some basic template meta programming. What's important is that in the API, the functions are typically written or declared in this fashion. So you have some function, and it is typically a template, and the types of the arguments are constrained by the meta object concept. So this is the preferred way how the API functions should be defined. But you can also use the requires clause if you want to do something more complicated. So then a reflection is a process, generally a process through which we obtain metadata or meta objects, and on which we can obtain the metadata indirectly through some reflection operations. Again, from syntactic point of view, this could be done through a dedicated operator or some special language expression. In this presentation, I'm going to use this mirror keyword. So this will be basically the placeholder for what the actual reflection operator will be. This is taken from a library that I have written, and I will go into bigger detail later. So some very trivial example would be I want to reflect the int type. So I used that expression, whatever is inside these parentheses is the reflected base level entity, and this returns a constant value that we can store in a variable. And the very basic thing that we can do with it is that we can check if the type actually conforms to the meta object concept that we have declared before. The opposite operation of reflection is colloquially called unreflection or splicing, or there were some other terms used as well. I'm going to mostly use unreflection or splicing. This is basically going back from the meta object to the entity that is reflected by the object. So basically getting back to a base level type that we use in declaration of a variable, getting the value of an enumerator, and so on and so on. Another example would be, for example, invoking a function or a constructor through some operation on the meta object, which is reflecting the base level entity. In more general terms, splicing can also mean emitting a snippet of code which somehow references the meta object and basically splicing it back into the program as if it were written by you as a normal program construct, but we can do some additional magic. If we reference meta objects, we can splice them back within that snippet of code and so on. But this is still in the future, and there are some use cases for this, but this is not something that's settled. So generally, what is a reflection API? It is a set of functions which are operating on the meta objects. And these functions can be classified or grouped into various categories depending on some criteria. For example, their use. So we can have some classification functions saying what we are reflecting, extracting some primitive pieces of metadata, having some operations on containers of meta objects, having some more complex algorithms which are still reusable, having some helper functions like predicates, comparators, transformation functions, and we can even provide some syntax sugar like placeholder expressions and so on. And again, most of this is done in the const-eval or constant expert context. So this happens during the compilation. The whole evaluation happens then, and you just get the result of the whole computation, which is done at compile time, then emitted into the program. So what would be the design considerations for a reflection API? Let me just stop here and clarify what the presented API here is. We have the reflection TS in standard C++, which is a temporary experimental part of the standard, which has a template metaprogramming API. This is considered sort of obsolete way how to do things. So now we have some other proposals. We have some sort of consensus on a const-eval API, and this is the thing that I'm presenting here is another alternative how the reflection API could be designed. So the goals here were to have a functional style API which has some clear syntax. It should support as many use cases as possible. It should provide not just basic metadata extraction operations, but also some algorithms, which basically algorithm library, which allows you to handle various use cases and patterns. And it should support composition of those algorithms and the basic functions into custom, bigger algorithms, which can be used in place where they are needed. Another very important things from the usability point of view would be proper interaction with argument-dependent lookup. So no excessive name qualification should be required, and it also should be similar to the STL and other libraries like Boost. So a very first example, how could we write a reflection-based Hello World program? We could declare an empty structure which is called hello, then we create an instance of that structure which is called world, and then we reflect both of those things. So here I'm getting a meta object that represents this structure, and here I'm getting another meta object that represents this variable. And a very trivial operation, one of the many that are available on such meta object is getting the name. So basically this thing prints hello world. So we have mentioned that the meta object operations are divided in several groups. So the first quite big one is the set of classification functions, which tell you what the meta object reflects or represents. So you have a lot of functions like reflects named, reflects enum, reflects record, reflects member function, reflects function call expression, and so on. And these return a Boolean value telling you like what is the base level entity that we are looking at. And this is typically used to constrain the arguments of a function, or they can be used in if const expert clause in the condition. The other big group of function is the metadata retrieval function. So these return the individual pieces of metadata which are useful for various purposes. And some of these functions are applicable to any meta objects, for example, getting the source location or comparing if two meta objects reflect the same base level entity. And some of them work only on specific meta objects. For example, the getName operation is defined only on meta objects that reflect something that actually has a name in the base level program. Likewise, the getType function only makes sense on meta objects which reflect something like a variable or a constant or a function, all of which have some associated type. So these functions can return values of various types. Many functions, as I mentioned, return Boolean values. Then you have functions that return integers like the get source line, get source column. Functions that return other constant values, for example, enumerator values or pointers and references. Then we have some functions which return strings, like get me the source file name or get me the name of the base level entity. Another group of operations can give you back the base level types that a meta object reflects. And then there is another very big group of operations where you, for one meta object, you get another meta object. So for example, you have some declaration which is made in a namespace and you want to know what is the meta object reflecting the scope of the original declaration. you can call this getScope function, and yeah, we will see other ones. So some slightly more complicated example would be like we have some sort of logging API. We have some where there is a representation of the log, and in the process of the logging, we want to write down what is the base level entity that is related to a log message. And one way how to do this would be to reflect the related meta object or meta object, pass it to this function, and then we can use some of the operations that I have mentioned. For example, I can check if that meta object reflects the global scope, I say this. Otherwise, if it reflects something that has a name on the base level, I can call this getDisplayName function, the prototype for which is here, and you can see that it returns a string view, and the parameter is constrained only to meta objects that reflect something that has a name. If neither is true, then I print something else, and then I have some operations that are applicable to whatever the meta object reflects, so the source file, the line, and the column. So these are the operations which give you the source location information. As I mentioned, we have several functions which can give you the name of the base level entity. So this getName operation is the most basic, and it will give you the immediate thing, the immediate name how the base level entity was declared. So, for example, if you reflect std string, you will get something like basic string. Then you have another operation which is called getDisplayName, and this if the compiler knows some quote unquote more user friendly or human readable name like an alias, you can get something like string. And then you have an operation like getFullName, which will give you the complete type name, including all the qualifiers, template arguments, and so on. And I forgot to mention, but most of this API is based on the operations like they were defined in the reflection TS. There are some extensions, but most of the API follows that original design. So then you have operations which give you Boolean values saying something about the specifiers and various decorators like constexpr, no except. Then you have other miscellaneous functions which can tell you, for example, if a record type uses the class key or the struct key, or is it a union. You can ask if a lambda capture is explicitly captured or in some other way, and so on and so on. Like currently, I think there is close to 100 of various metadata retrieval functions. Then another group of functions which is actually doing the unreflection or splicing are these ones. So, for example, you have a meta object that reflects a constant like an enumerator. You can get back the value of the constant. If you have something that reflects a variable, you can again get the value of the variable. You can get the variable of a record member in some particular object. You can get a reference to a variable. You can get a reference to a data member in a particular instance. You can get the pointer again to a variable or a data member. And you can also invoke various callable base level objects like functions, member functions, operators, constructors, destructors. So you can specify what is the meta object that reflects the desired callable, what are the arguments, and then this will be invoked through a unified API. So then the last group, I think, is the one that I mentioned already, where for one meta object, you get another meta object. So I already described what this getScope is doing. You can get a type of a variable. You can get a class from base class specifier. You can get a sub-expression from a bigger expression that is reflected, and so on. And again, these are not all the operations which are in the API. There's way more. And these operations allow you to get back to the type which is reflected by some sort of meta object. So if the meta object reflects a type, you can get back the type identity with the template parameter, which is then the base level type reflected by this meta object. And if you are familiar with libraries like BoostHANA, for example, and other template-based const eval or const libraries, this is quite a common pattern where you use this type identity as a representation in some type, and you go from basically a value-based world to types, and you can do some manipulation of those types in some functional style algorithms, unlike in TMP, where you would use templates or template aliases. Okay, so then the last type of meta object that I didn't mention in bigger detail are meta object sequences, and these are basically containers of other meta objects. And for various reasons, it is useful that the meta object sequences are meta objects themselves, and they are returned by many operations in the API. So you can get the base classes, all the data members, all the member functions, enumerators or parameters of a function, and so on. And one notable thing about the sequences is that when you get the meta object sequence, the elements of the sequence are not immediately materialized. So if you, for example, reflect the big namespace like namespace boost, which can contain like thousands of declarations, and you only want to check, okay, is this namespace empty? You don't need to materialize all the meta objects. You want to do this only later and only if it is necessary. So again, these are some of the functions that return sequences. I mentioned get base classes. You can get the captures of a lambda. You can get the constructors of a class. You can get the destructors. You can get the enumerator values, member types, operators, parameters, and so on. And the basic operations on the sequence. The first one is identifying is a variable of some type actually a meta object sequence. So this returns true or false, depending on if the argument is actually meta object sequence. Then you can check if the sequence is empty, what is the number of elements in the sequence. You can get the individual elements. If you have multiple sequences of meta objects, you can concatenate them, and there are some other operations we will see in a second. So one of the most trivial operations on a meta object sequence is for each, which does basic iterations. This is basically the same, at least in functionality, to std for each. So you have some meta object sequence, so a container of other meta objects, and you want to call a function on each one of the elements. So for example, I have an enumeration of weekdays. I want to get all the enumerators. I reflect that enum. I want to get all the enumerators which are in that enum type. And on every one of them, I want to do this thing. So I want to get the name of the enumerator, and I want to print the value of the constant as an integer. Another thing that I mentioned before, this is basically syntax sugar, are placeholder expressions. So this is nothing new. We have seen placeholder, and we have placeholder expressions in various Boost libraries. We also have them in the standard library now. So there are some constant objects which are called, their names are spelled like this, so _1, _2, and so on. And then you have expressions where the expression takes one of the placeholders as one of the arguments. And what the placeholder expressions do is they don't actually immediately call some sort of reflection operation. They create a callable object like a lambda that can be called later. And the reason why we have the placeholder expression is that lambdas are nice and they have really short and nice syntax. But with the placeholder expressions, you can shorten the expressions even more. So basically, this could be viewed as laziness, but I think that in many cases they also improve the readability. So there is some syntax in the lambdas that sometimes gets in the way of understanding what's happening, and the placeholder expressions help with that. So really quick how they are implemented. So there is some template which is called placeholder exper. It has some function which is stored somewhere inside. It has a call operator. Then you have these two placeholders, and for every actual reflection operation, so this would be an actual operation like get name, get type, or whatever else, you have another overload, which instead of a meta object takes the placeholder expression, and it basically returns a lambda that can be called later with an actual meta object. So some very simple examples of predicates. So I can create a lambda that will later be able to check if a meta object reflects something named, if it has a type. So you can compose them into more complicated things. You can have some comparators, so you can check do these two meta objects reflect the same base level entity? What is the comparison of the name of the left and the right, and so on. And again, all of these do not do any immediate reflection operations. They just return lambdas that can be used later. And so the last big group of placeholder expressions are various transforms, and here you can see that you can do some pretty complicated things. So, for example, this can be a placeholder for something that has a type. You can get the scope of the type, you can get the name of the scope, and you can get the length of the name. And this is, if you try to do this as a lambda, it will be like more typing. Okay, so then why would be all the things that we mentioned before, or how can they be used in some bigger things? And this is where algorithms come into play. So they implement some small specific pieces of functionality, which is not really trivial, but it is reusable, and it can be combined into various even bigger things. And these algorithms are based on the primitive meta object operations that we have seen before, and they can be combined into custom algorithms in place as they are needed. They can interoperate with the placeholder expressions, and most of the so again, some example. transform algorithm, what it does, it takes a meta-object sequence, so a container of meta-objects and some sort of function, transformation function, and it goes through all the meta-objects in the sequence and calls this function and returns another meta-object sequence that contains the transform meta-object. So some example. There is no operation in the API which is called get parameter types, but you can very easily create one if you need it in place. So you get the parameters of something which will be specified later. Then for each of the parameter, you get the type of that meta object and you tie it together with the transform algorithm. Similarly, you want to get the base class type. So when you call this function base classes, you don't get immediately the types of the base classes. You get a meta object that combines the type of inheritance of virtual or not virtual, the access, private, protected, public, and the actual type. And if you want to extract just the type, you need to call this get class function, and this is how you can use it together with the transform algorithm. Then you have things like filter, which takes a sequence and a predicate, and it returns a new sequence which contains only the meta objects which satisfy this predicate, or remove it, which is the opposite. So for example, I want to define an operation which will give me only virtual functions. So again, this is a placeholder expression, so this can be specified later. For whatever it is, you get all the member functions which are there, but we filter only those for which is virtual returns true. The same thing for non-static data members. So you can get the data members of something, and you remove all for which is static is true, and you get only the non-static ones. Same with countif. This is pretty trivial, so you can count something depending on, for example, if it is public, or if like a data member has a specific type trait, and so on. Then you have some search functions. So find if and find if not return to you the first meta object in this sequence which satisfy or doesn't satisfy this predicate. So you can, for example, get all the member functions of some class, and you want to find the first one for which the name is full, or again, get me the first data member which is non-static in some sort of class. Then this find ranking operation is similar to what we have seen before, but it is slightly more complicated. And what this is doing is that it again takes some meta object container. It takes a query function and a compare function or comparator, and it takes every meta object in this container. It calls this query function that will give you some piece of the metadata, like for example the get name function or something else, is static, is virtual, and so on. And it will compare the returned values by these other functions, and it will give you that meta objects for which the value according to this comparator is the largest. So an example of how this could be used is that I want to get the data members of some class, and for each of the data members, I want to get its type, the reflection, the meta object reflecting its type. I want to get the size of that type, and this operation will return to me that meta object for which this expression returns the largest value. This get top value does basically the same thing as the find ranking algorithm, but instead of the meta object, it will return to you the actual value that you are checking with this query function. So in this previous case, the result of this would be a meta object. In this case, it would be the metadata taken from that meta object. So again, I want to check what is the maximum number of parameters in all the member functions of some class. So I get all the member functions. I get the parameters of each one of those member functions, and I check how many are there of them, and I want to get the maximum value of that. Again, we will see some more concrete examples. This might seem like why would I want something like that? But there are quite a few use cases where this is some thing that you need to solve in order to do the bigger things. So we will see some examples. So generally, I think you get the idea. We don't need to go through all the algorithms. There is quite many more of such algorithms like fold, join, is sorted, sort, and so on. All of, any of, none of. And the idea behind all of them is that using you could do all of those things that I have shown you before by writing for loops, for example, or template for loops. But having named algorithms improves the readability of the code. So if I have like 3 nested template for loops of some sequences and meta objects, and I'm doing some comparisons, it might not be immediately clear what the piece of code is intended to do. But if you do that composition of named algorithms, the code becomes much more readable. And usually it also requires way less typing. And the third quite useful thing is that many of the algorithms can hide some compiler magic that you shouldn't probably use directly, like in end user code, but you can hide them in for example in the filter function or in the transform function and so on. So as we have seen, one of the very important things of those named algorithms is that they can be composed in place, like from some smaller pieces into something which doesn't make sense to maybe doesn't make sense to have a specific API function, because maybe only one person of one developer of 1,000 will need that. But the composition of the small pieces allows you to create such algorithms on the fly in the place where they are useful without like defining a really big API trying to cover every use case. So some examples. I have these 2 enumerations or whatever enumerations, and I'm interested in testing if the enumerators are consecutive, the enumerator values. So here in these digits, this is 0, this is 1, and so on. So these are consecutive. These are power of 2s. These are not consecutive integers. How could I test if this is valid? So this is something pretty specific, and it might not make sense to have such operation directly in the API, but I can create that operation very easily. So again, this is done as a placeholder expression. So whatever this will be, I want to get the enumerators from the meta object, and I want to test if the enumerators are sorted according to this predicate. So if they pairwise, if for all of them this is true. So the value of the left enumerator is the same as the value of the right enumerator -1. And then we can use it several times like for the digits, it will return true. For the power of 2s, it will return false. You can want to, for example, you want to print some sort of table, and for that you need to know what is where in that table you are printing enumerator names, and to do proper alignment and padding and whatnot, you might want to need to find out what is the enumerator with the longest name. So you can use the find ranking algorithm. You get the enumerator, the individual enumerator values. You get the name of each enumerator. You get the size, and you return that meta object for which this expression returns the largest value. And then you can call it in several different places. And when you find that enumerator with the longest name, you can do some other things on it. So you can get the name of the enumerator, you can print its length, and you can print its constant value. So again, I have this weekday enumeration, I have this month enumeration, and I can use that algorithm that I just constructed to print, to find that information and to do something with it. Another example, does a class have overloaded functions? So there is this group by operation, and that group by operation, what it does, it takes some container of meta objects. In this case, it is member functions. And for each of the elements, I want to get the name, and then I want to create subsequences such that the meta objects where this get name is the same will be grouped together, and this will return a sequence of other meta object sequences where they are grouped by their name. And a class has overloaded functions if there is such a subsequence where the size is bigger than 1. So there are at least two functions in a group where the name is the same. And I test if this is true by using this Enum algorithm. And like here it is 7 lines. If you tried to do that with for loops and whatnot, it definitely would be more code. Or yeah, very, very possibly. So again, we have these two examples. This one on the left side does have some overloaded function. Here there are no overloaded functions. You call it on the left one and on the right one, and here you get true and here you get false. Another use case, I have a structure and I want to check if there is some padding. So we can approach this like testing if the size of that structure is bigger than the size of all its data members. So what you can do, you can use this transform algorithm, or okay, let's get even deeper. So you have this type T, you reflect it, you get the data members of that type. Then you filter only those which are not static. Then for the ones which remained, you can transform them by, you don't want to have the data members, you want to get the types of the data members. And then from all those types, you want to extract the base level types. What this extract types operation does is returns to you this type list. And then just by like pretty trivial meta programming with a fold expression, you sum together the size of and you compare it with the size of the whole structure. And if this is bigger than the result of this, then the structure has some padding. So again, we have some examples. This one on most platforms shouldn't have any padding, but here we have this char, and then it is followed by double, which requires some alignment on some specific alignment on many platforms. So very, very probably for this structure, this algorithm will tell you S1 doesn't have any padding, but this one does have some padding. Another example, we can check, are the data members sorted by size? Again, I get the data members and I compare if piecewise or pairwise the data members as we go from top to bottom, if for each one of them this operation returns true. And again, you can check. And for some more concrete and more usable use cases, because the previous ones might have seemed slightly esoteric. So let's have a look on something which might be immediately more useful. So I want to implement enum to string operation. So the parameter is some sort of enumeration type, and I want to return a string view that is the name of that particular enumeration value. So again, I have this choose algorithm, and this choose algorithm, it takes all the meta objects in this sequence. So in this case, all the enumerators of this type E, and it chooses the first one where this is true. So the enumerator that we are testing has the same value as the value that has been given as the argument to the function. And it doesn't just return the meta object, or it doesn't just return the value. There is another operation, which is the actual result. So for all the enumerators here, the first one where this is true, for that one, call this getName operation and return that. And this first parameter is the fallback. So if for some reason it happens that this has value operation, if it returns false for everything, then this value would be used as a fallback. So you would get a empty string. The other operation is basically the same. So if you look at them, they look the same way. So I don't think it is necessary to explain this. Only these two things are switched, and the return value is an optional, and the parameter is a string view. Okay, another one. This is slightly more complicated, but let's say that we have some C++ representation of the program arguments that you get in the main function. So this program arg is a single argument. It has some utility function, like what is the next argument following this one. Then you have these program args, and this is the whole set of the arguments. And then you can do the nice C++ iteration of that. And what I want to do is, I have these three things. These are some generic things, and I want to implement a generic function that will work on whatever structure that will take these program arguments, and it will try to parse the options into this object, regardless of what is this type T actually. And here we have some application-specific things, which can differ between various applications. And let's say that I want to write a very simple application, sort of like hello world, but it will print the message multiple times. So we have the actual message, we have how many times we want to print it, and we want to have some delay between each of the printouts. And I want to have this generic, or use this generic parse function to take these program arguments and to automatically parse them into the structure. And I don't want to implement it specifically for every such structure, because they can change even between different versions of an application, or can be completely different in different applications. So how would I do that? So what I could do is that I could use this program arguments class that we have seen before. I can go through every argument. I can use this range-based for loop to iterate through the arguments. And within that, there is another nested loop where what I'm doing is that I go through every data member in this type T, in the type into which we are parsing. And for each one of them, I am going to call this function. And in this function, I get the name of the data member. I somehow compare it to the argument that I'm currently testing. The details are not really important here. And if I say, okay, this is an argument that I'm interested, this might be something that I can parse into the structure. I want to take the next argument, and I want to call this from string function that will parse the value of the argument. And this from string function needs to know what is the actual type of the data member. So again, I take this metadata member, I get its type, and I get the reflected type. So this is another example of the splicing of unreflection of the reverse operation. And you can have multiple different overloads, some for integers, some for floating points, some for chronotypes, or for whatever types you want to support. And you use this the result of this operation, which is again the type identity that we have seen before, to choose which of the overloads of these from string operations you want to call, and then you parse the string value that you get from the argument. If that was successful, then you use another reflection operation. So again, you take the meta object reflecting the data member. You get the reference within this object, and you assign the parse value. Otherwise, you print an error message, and you are done. Another use case, you have something like virtual interfaces, many of them, and you want to track the changes in the operations within the virtual interfaces. So you want to know if somebody, for example, adds a new operation, or if they change parameter value, number of parameters, return value, and so on. And you want to produce some sort of hash which uniquely identifies what is the API of that template interface. And again, the question is how could you automate this? And again, the answer is with reflection. So you basically reflect that interface, you get the member functions of that interface, you take only those which are virtual, because these are those that you are interested in, and for all of them you use this get hash operation, which basically calculates an unique hash of some of the base level declaration that some meta object reflects. And what this thing does is basically this makes the hash of the function itself, and this makes the hash of the return value of that function. This takes care of all the parameters of the function, and you combine them together. And then this fold operation, what it does, it is sort of similar to the transform operation, but it is more generic. And it basically combines all the hashes. So for all the member functions, you filter out the virtual ones, you calculate the hash, and then you combine the hashes into a single value, which you then return. And this is what represents the revision ID of the interface. So a use case, I have this interface which initially looks like this, and it inherits from that template that we have just seen, and it has these three operations. And when you call the revision ID, then you can get, for example, this value. And sometime later, you do some changes. For example, you change this parameter type, you change this return type. And then if you call this revision ID operation, you will get a different result. And this is useful, for example, for checking between two different translation units. If you are dealing with the same operations and if it didn't change, or if it doesn't have different definitions in the different translation units. So you can, for example, do such checks. Okay, another slightly bigger example is implementation of some parts of RPC. So in remote procedure calls, you typically find classes like this. So you have some sort of interface that you want to call remotely. You have some stub, which is some local representation in the process where you are calling that operation. You have something which is called a skeleton, which is the counterpart on the remote side, and then you have the actual implementation of that interface. And basically, the sequence diagram for a synchronous case, you typically don't do this synchronously today, but to simplify this, the sequence diagram would look like this. So you have a user that through the basic interface calls the stub. There would be some stub implementation which will handle the serializing and so on. It will pass the serialized request to some connection. The connection will transmit it to another process. Then on receipt of the data, this the skeleton class would be notified. Then the skeleton class needs to unpack the request. It needs to find what is the actual function that is being called. It needs to create some space for the deserialization of the parameters, then call the actual implementation, get the return value, serialize the return value, use the connection to transmit it back to the stub, and here it is deserialized and returned to the client. And this is typically currently in C++ handled by code generators. So you have some interface definition language, and you generate all the code for these stubs, for these skeletons, and so on. All the dispatching, searching for the function, serialization, deserialization is typically generated code. And we can, if we had reflection, we could actually implement a lot of these boilerplate code like through metaprogramming. So let's say we have this interface like a calculator with some operations like add, subtract, and so on. And the question is, how could we automate the implementation of the stub? So what could we do is that we inherit from the interface and we implement all the virtual functions within that interface, and we basically everywhere we use this same pattern. So we have some sort of helper class that has this function called make call, and it takes something, we will get to it later, and it takes the parameters. So for the add function, you call this make call function and you give this add LR expression. For subtract, you do the same, and you would do the same for all of these. And the question is how to do this RPC stub implementation generically so that it works for whatever interface that we are using this on. So this is just a pseudocode and it doesn't show all the details. But what the make call operation could do is that it would take a meta object that reflects an expression. So what is happening here is that I make a function call expression and I reflect that expression. And the reason why I want to do this is that I want to get the sub-expression, the actual function call sub-expression, which is happening there. From that, I can extract what is being called, so the callable, that particular member function that is called. I want to get, for example, the return type. When I'm deserializing this, I want to get the return type. And I want to splice it back so I can get this type identity and I can properly deserialize it. So I'm not going to show the details here because that would be pretty long, but again, in this deserialize or in this serialize operation, you could use reflection and automate it for quite a big chunk of user-defined types where this would be applicable. So on the other side, so in the skeleton, on the side of the remote process where the dispatching needs to be done, you have some sort of virtual interface like this with this dispatch method, which takes some request packet and some response packet. And again, how the dispatch function or that skeleton could look like. It would have some pointer to the actual implementation. You would need to extract the method ID that is being called by this particular invocation. And then you take all the member functions from that interface. And for each one of them, you call this function. So you get the method ID that you have extracted from the request. You compare it with some calculated method ID for each one of the functions in that interface. And if this matches, then you can again use this transform function as we have seen before. You can use it to create what this operation does is that it creates a tuple into which you can deserialize the arguments for the call. So this will basically create a tuple with the same parameters as are necessary for making the call to the function that we've found and identified. Then we can do the deserialization into the parameters tuple. This is another meta object operation which basically takes the reflection of the member function. It takes the object on which we want to call that particular function, and it also takes the deserialized parameters. So this is basically as if you typed in the expression for calling that particular function. You get the result, you serialize it, and you send it back. So this is again quite a few reflection operations, and this way basically you could make the skeleton generic and reusable for many different versions of this interface type. Okay, so this is a sort of funny one, so don't try this at home. But one thing you might want to do with reflection, maybe not exactly like this, is that you want to define your own concepts depending on not just type traits, but on some metadata that you can get back from reflection. So what we are doing here is that we are defining this integer concept, but we don't want to use the basic type traits because they are boring and they include, for example, the Boolean type, and we don't want the Boolean type. We want only those types for which the names conform to this compile time regular expression. So if it is just the name int, or it is the name int with all these decorators like signed, unsigned, long, short, and so on, then this type T conforms to this concept. And then we can use that concept in a function. And for example, in this case, I don't want to add Booleans. So I only want to add types for which this regular expression matches. So it will work with unsigned types. It will work with shorts. It will work with regular integers. It will work with unsigned longs, but you won't be able to add true and false, which do not conform to this. Okay, so the last thing that I mentioned before we conclude is that before we have seen the API where you have the individual functions, like we have seen the function definitions, how they are defined. But for some use cases, it is quite useful to have another API. So in this API, you don't have many different functions. You have, for example, just this one function, which is called the has trait. And all the Boolean traits of meta objects are actually represented as enumerations in an enum class. And then you don't call multiple different functions. You call only this one function, and you the trait that you're interested in, you specify as the template parameter for this one. Then for the other operations like get name, get type, get enumerators, you have these three functions where you first can check is that particular operation like get type applicable to this meta object. This will return to you a Boolean value. If it is true, then you can apply that function and you will get some result. Or you can combine these two into this try apply function. And if this particular operation like get name is applicable to the meta object, which is the parameter of the function, then that operation will be called and you will get that value in an optional. If that operation isn't applicable, you will get an empty optional. And one of the use cases where you might want to do this is something like you want to print all the traits of some base level declaration, and you don't want to spell them one by one. You might miss some might be added, and so on. And you want that program to be future proof, and if somebody adds new operations to this enumeration or to this enumeration, you want it to keep working. So what you might want to do is that you actually reflect this set of enumerators, each of which represents a single meta object trait. So then you get all the enumerators. You get the longest value. This is just for padding for the output. So this max value is used to print as many spaces as necessary so that the other column is properly aligned. But what you are doing here is that you are taking all those operations that are all those traits that are defined currently in the API, and you just call that single generic function, which is called has trait, and you call it for each one of those operations which is in that API. And so the result, for example, if you reflect the stud string type, you will get a really long list of various trait values. So that basic declaration is named. It is an alias because it is an alias for basic string. It is a scope itself. It is a scope member, and so on and so on. So this is another API which is more generic and more useful in certain use cases. Okay, so I have tortured you quite long enough. So from my side, having played with reflection for years and years, I would say that reflection can be really fun. it is definitely very useful. And it is possible to create a reflection API where the code is readable, it is easy to write and easy to understand. And it also provides not just some trivial operations, but it gives you also some toolkit of reusable algorithms that you can combine into something bigger as you need it. So there are a lot of use cases. I actually have another presentation going through 10 different use cases, most of which are listed here in some bigger detail. And yeah, so where can you find the code that we have seen here? So there is this mirror library. The current incarnation is on GitHub. This is like the 7th reboot since 2006. It is implemented on top of the reflection technical specification implementation, which I've done in Clang. So you need to build your own fork of Clang, but it is not really complicated. You can use a script which is included in that repository. And it basically contains all those things that we have seen before. There are some use cases which are bigger, which don't fit onto a single slide. There are many use cases. There is integration with other objects like or other projects like the compile time, regular expressions, the Chai script, scripting engine, and so on. So these are the links. The presentation itself, it's on GitHub. It's basically my name /mirror. Yeah. Maybe just to mention how is reflection going to look like in C++? We, as I mentioned, we have the reflection TS, which was sort of dead on arrival. It was replaced by some different API. There are still some discussions or contentions whether that API, how it will eventually look like. So we have presented here, or we have seen here one possible option. And what's next for reflection? I think definitely more splicing. One very useful feature would be the ability not to just splice a single type or a single value or a single namespace, but to splice whole fragments of code which are referencing some meta object. Another thing which is sort of planned is splicing identifiers. So you would be able to create your own identifiers depending on somehow on meta object and supporting more use cases. So yeah, thanks for your attention, and let's look at any questions that you might have.
Thanks for the great talk, Matúš. That was really interesting. During the beginning of the talk, Daniela asked an interesting question, but I think we're gonna switch over to Hubilo into the questions room. That's probably for everyone. And so thank you for your talk, and let's have the questions in Hubilo.
Okay, see you there.